grab screen share here. All right, you guys should be able to see this. Hopefully my internet is not horrible and the delay won't be too bad. Cool. So I will get started. I have chat up over here as needed. Cool. So my name is Jason. Currently, I am a kind of a first-year PhD student in robotics at Georgia Tech. I've been on Robotics for a couple of years, so I've been around. Most of my research is around stochastic optimal control, so not really machine learning, but we do a lot of learning on top of our control. So briefly, I just want to talk about kind of the motivation of what these meetings are and how they're different than the C++ ones, C++ ROS ones. So here, I'm going to be covering a lot of topics. I'm taking like what is weeks of coursework and condensing it really finely and kind of skipping a lot of details somewhat arbitrarily in order to give you kind of an overall picture of what this concept of machine learning is. And this, hopefully the pattern will continue throughout the rest of the weeks. So you'll get kind of a familiarity with the topics that people use and the vocabulary that we use whenever we talk about these kind of topics. So if you don't fully understand everything that I say and everything, like every little nuance of every topic that we discuss, that's totally expected. I'm speeding you through a bunch of things that you really shouldn't speed through. The main question that you're supposed to get out of this is the ability to ask the questions that you need to ask correctly. Because a lot of people come into these things, like these kind of more complicated topics, and like, I don't even know where to begin to ask my question. Hopefully this presentation and the presentations following will give you the necessary vocabulary and the general high-level understanding of what's going on, like what are the ins and outs of what we're talking about, in order for you to be more effective moving forward. So that's kind of my take on why we're doing these meetings, and hopefully it works. Someone say something? I think it was just my echo. Cool. So we're going to be talking about machine learning today. First, we're going to talk about supervised learning, then we're going to talk about unsupervised, then we're going to talk about reinforcement learning, and then we'll go back to a little bit more detail on supervised. So before we get into that, I'm going to cover some notation really quickly. There's not going to be that much math in this presentation. I intentionally didn't do that, but here are just some really common notations that you'll see. Someone. Okay, I don't know what happened there. I bet my screen share died too.
It did.
Okay, so not that one. Okay, you guys should be back. So we're going to talk about vectors. So what you're seeing down here is we have this notation. So we have a vector that belongs in R3. So this symbol represents the set of all real numbers. So it can be essentially any arbitrary number you can think of off the top of your head is most likely a real number. So we have a vector. So we have a vector of belongs in R3, and all that means is that I have three numbers that you can think of as one unit, and that's what we call a vector. This is the mathematical definition of vector, not the programming definition of vector like you covered on Thursday. So if we have a vector that belongs in R3, this is a typo, it should say R2 with dimension of 2. There's also, slides. So what you also have here is, this is a function. So you'll see this kind of notation pretty frequently. So we have a function, it takes in a vector x, and then it's going to output some vector, usually called y, which will be of a different dimension. So you take in one of dimension n, and you output one of dimension m. And that is kind of the important part of what you're trying to do here. So this is just some notation that will come up more when we talk about RL really quickly. So what is supervised learning? So really there's two kind of takes of supervised learning, but essentially the overall goal is that you're trying to learn some sort of function. You have an input, which is a vector, which can be made up of whatever. It could be like RGB values of a pixel. It could be what are the actual like stock values of certain stocks, whatever it is. It can be completely arbitrary what your input is. But the key part about supervised learning, why it's called supervised, is that you actually know what the direct output is that you want to see. So I have some input vector x, I have some output vector y, which is known. And what I'm trying to do is teach my machine learning agent to take in the x and output the correct y. And then what I want to do is give it new x's that I don't know the output to and figure out what the output should be. So there's two classes. You have classification. So this is a discrete output. So like, is there a cat in this picture? Yes or no. Essentially, there's a finite number of things. You also have regression, which is more general, like fitting a function. So you have a continuous range of outputs that you could potentially have. Again, to just stress it, you know the answer of what you're trying to figure out. Hopefully this graphic is better. So we have some sort of data set. We have our input vectors x. We have the corresponding true value y. And what we're doing is we take our input vector x, we apply our machine learning thing to it, our supervised learning algorithm. We output some prediction of y hat. And, you know, that's hat is just a little caret on top. You'll see that notation pretty frequently. Then we have this true prediction, which we know from our data set. And essentially what we're trying to do is find the difference between these two, and then we use that to update this machine learning thing in order to make it more accurate over time. So we're learning from our experiences. Since we know for every given input, we know what the output is, we can just find the difference between the two. And all we're trying to do is just match this function exactly. So that's supervised learning. So what is unsupervised? So unsupervised essentially means you don't necessarily have a label. So this is more about understanding your data and looking for patterns in the data set. It's also a thing called dimensionality reduction, which you'll hear a lot. And essentially what it means is, let's say I have 10 million possible features. Like, let's say I'm trying to predict the Dow for tomorrow. I need to have the stock price of everything in the Dow plus essentially as my output. And then my input needs to be essentially all stocks and a bunch of other things that relate to stock prices and how they all connect and come together. But that's just an insane amount of data. What we'd like is less data to work with, and you can use unsupervised learning to kind of reduce dimensionality, so the number of inputs that you have with it. So here's a classical example of it. It's a thing called k-means clustering. You get that? And essentially what we do is we have all these data points in the xy plane. We have these cluster centers, which are represented by the colored points. And what it's going to do is it's going to start assigning these points to whatever cluster it's closest to. And it'll do one iteration of that. And then as soon as that's done, it'll move the center of the cluster to the center of the points in the xy plane. So if I took all the points and averaged their x values and averaged their y values, that's where I put the center of the cluster. And what you'll see is over time, it'll start to be able to distinguish between these general clusters of data, which like you and I could have pretty easily predicted where the clusters are and put these initially, since this is a 2D example, but we're talking about dimensionality in the tens of thousands sometimes. So it gets a little bit more unclear what does a 4D thing look like relative to like anything. So k-means is a pretty cool algorithm to do simple clustering. But then what is reinforcement learning? So essentially, keeping on the same theme of what we have, we're trying to learn from our experiences. So usually what we're trying to figure out is what action should I take given I am in some state? And actions are obviously arbitrarily defined, and so are states. So for like a robot, like with my autonomous driving research, our state is like, what is the x position of the robot, what is the y position, and what is its heading, what direction it's pointed effectively. And we're trying to figure out what steering and throttle angle should I give my car in order to go as fast as possible, or whatever else we're trying to do. So this gets a little bit more complicated because every action doesn't, if you are in the same state and you apply the same action, it doesn't always give you the same state. And this is called stochastic state transitions. You'll hear the word stochastic a lot. It's my favorite word. My parents say it all the time to make fun of me. So essentially what that means is random. So whenever you hear the word stochastic, you can immediately think that it's random. So we also have this thing called a reward function. And essentially it is how good is it to be in a state. And then at the end of the day, all we want is to figure out what action should I take in every state in my entire state space and what action should I take from that state? So in a little bit more mathematical formalism, what you'll see here, so what I'm saying here is there's a vector x, which belongs to the set of all real numbers of dimensionality n. So this is our state. You'll see x will always usually represent state, a is action, and whatnot. So we have n possible values that could represent our state. So for driving, this could be x, y, theta, which represents your yaw angle, which is your heading. And for our actions, it could be like steering throttle. So this would be x belongs to R3 and a belongs to R2, as an example. So then we have this thing pi. So this is our policy, and this is that function notation we talked about. So what you're doing is you're taking in a vector in n, so it could be it's a state, and then you're going to transform it into a vector in m, which is what the dimensionality of our action. And this is essentially saying, given an arbitrary state, what action should we take? That's it, just mathematically writing this out. So we have a reward function here. So this takes in a state and it outputs a real valued value, which is our reward function, how good the state is. We have this transition. And what this notation means right here is that you're taking in essentially two vectors, one of n and one of m, and you're transitioning into a new state in space n. So essentially, I put in my state, I put in my action, what is my next state? You have the same thing with the value function. The value function is very similar to the reward function. It's just the expected reward that you'll get if you follow the optimal policy from the state. So this is, reward function is for only one time step, and the value function is for all time. You'll see this kind of formalism really often if you start looking at RL. We're not going to go into it in a lot of detail, but I just wanted to give you guys the basic notation so that if you start looking at things online, this notation immediately pops up, and I didn't want to get confused because I used to get very confused on this. So kind of an example of reinforcement learning. This is my favorite just because it explains the point well, and it has amazing graphics. Researchers suck at having good graphics. This is from Google DeepMind, and essentially what you're seeing here is, let me not go full screen, make sure I can still see things. So you have the guys in blue and you have the guys in red. And what they're trying to do is a surveillance task. So the guy in red is trying to always view the guy in blue. He gets reward from doing that, and blue loses points if red is seeing them. So essentially what they're trying to do is keep red out. So what they kind of learn how to do is they can use these blocks that they can lock in place that red can't unblock or can't move. And then they can no longer be viewed because red cannot see them. And over time, it'll learn more complicated things like learning to block new doors. And the key part about this is that no one ever told them to block the doors. We just told them what is bad, which is being seen. Don't be seen. Here are all the actions you could possibly take, and then they figured it out from there. So what red learns to do over time is to use that ramp to jump in. Obviously, what blue's going to learn immediately right afterward is just if we take the ramp inside, they can't use it to jump over the wall. And you're like, oh, this is such a simple task. And they're going to make it more complicated in a second, but this is kind of the general of what reinforcement learning looks like. And this is millions, if not hundreds of millions of iterations in order to get to this point. So now what they're going to do is create structures entirely from movable obstacles. So they'll barricade themselves in right here. And as you can see, they also locked the ramps. Because if they didn't lock the ramps, the red would just use the ramp to jump into their structure. Once they lock it, red cannot unlock it. And what you're going to see here is what happens really often in RL, especially with your own simulator, is that it learns to do things that it shouldn't be able to do. So what it's going to do here is exploit the physics in order to jump on top of a box and then use it to push that around the map in order to jump in to the actual structure. But since they've learned that new strategy, what blue is immediately going to learn how to do is just lock everything down so they can't do that in the future. And then they win, because there's nothing else that you can do with respect to these dynamics and physics. And then just at the end here, they're going to show you kind of a visual representation of how many thousands, if billions, millions, trillions, whatever large number you want, of iterations they run. And this is kind of why Google does so well, because they just have the compute power to do insane amounts. So let's talk about some common supervised learning. So remember, supervised learning is when we have some data set, which both the input and the expected output. So probably one of the more simple ones to understand is this thing called a decision tree. And we have one pictured here. Essentially, we're trying to classify animals. And what you're going to do is at every node, so leaf nodes are nodes at the bottom. These are actual classifications. You have questions, essentially, at every point, and you do branching. So let's say we have this penguin. So a penguin, does a penguin have feathers? Yes, it does have feathers. Can it fly? No, it cannot fly. So therefore, this image is a penguin, based on the features that we have that define a penguin. So you can do pretty interesting things with decision trees. So here's an example. What we're trying to figure out is this arbitrary mapping from numbers on the left to map numbers on the right. So there's an actual true function that's generating these numbers that I won't tell you. And we're going to learn something about machine learning. So what you're going to do here is what we want to do is look at all of our data. We want to classify as much data as we can at step 1, because this gives us a shorter decision tree, and therefore it's faster to look up the actual answer on average. So we see we have 4 values of 0 based on the inputs of 15, 12, 21, and 18. Sorry, that keeps popping up. So what's a simple rule that tells us anything like if 12, 15, 21, and 18 are all 0? Well, if x is greater than 12, x greater than or equal to 12, it's 0. Otherwise, it could be 1 or 2, based on the data set that we have. So now we do the same thing at the next level. So now we have data that goes 1 and 4 that maps to 1, and 8 and 5 that maps to 2. These two have the same amount of number of examples, so we can just split them anyway. And what we end up with is if it is less than or equal to 4, actually I messed up, and if x is greater than 4. So now we have this decision tree that perfectly classifies all of our data. Now, what if I give you a new example, which I have is 2 maps to 2. So let's see. Is 2 greater than or equal to 12? No, it's not. It's less than 12. Is 2 less than 4? Yes, 2 is less than 4. Therefore, according to my decision tree, the output should be 1, but it's not. So what we saw was a really good example of incorrectly, there's 500, sorry, of essentially bias in our data set. We only saw a limited number of examples, so we only learned what we saw. But since what we saw didn't represent the actual underlying function in any meaningful capacity, we could make decision tree rules that perfectly classified every point in our data that did not map to the real world at all. In fact, they were completely wrong and would lead us astray. So you can also do other things with the decision trees. You can do things like, you guys can't see this share screen thing, can you? I'll just leave it over there. So we can do other functions. Pretty much at any node, you can arbitrarily shove in different mathematical functions, different classifiers. You can do, like, you can put a neural network at any one of these. Like, there's a multitude of things you can do. You can start combining these things together. So the actual true underlying function of what we saw previously is I'm just taking mod 3, which just represents, essentially, if I took the number and divided it by 3, what is the remainder? That's it. So 1 is 1, 4 is 1, 12 is 0, 8 is 2, yada, yada, yada. So like this is a perfectly valid decision tree that also classifies the same data that I did before. But this one is perfect because it actually represents the underlying function correct. So this is kind of the issue with machine learning. If I know what function I'm looking for, I can represent it really easily, and then you get really simple things like this that can represent this data. But usually you don't actually know the underlying, like what the underlying function that is generating your data is, so you kind of have to guess at it. And this is where the actual like complicated part comes in. So I'm sure you guys have seen neural networks, or at least heard about the name, heard the buzzword. They're really popular at career fairs for people to be like, neural networks, neural networks, neural networks. You're doing deep machine learning in the cloud using blockchain or whatever. So this is what a neuron looks like. So when we first started looking at neural networks, it was back in the 1960s. They took like 40 neurons, took a supercomputer, put 40 neurons, tried to predict something, and they're like, this is useless. This is crap, because it doesn't classify anything that we need that is useful. So they kind of abandoned that for a while. Now, most of you that are thinking about your brain, which is what the analogy is, has billions of these. So obviously trying to do something with 40 is not a great way to do complicated tasks. And this is what happened. It was just purely based on computational resources. They kind of abandoned this because it wasn't useful or practical at the time. But now that we have billions of transistors or cores that can do insane computations quickly, it becomes a lot more efficient, and especially with the evolution of the GPU. So what you're going to see here is we have our input. So this is just like our normal vector that we've had before. So it's a vector in Rn. We have n weights. We take each input, we multiply it by the weight, we sum up all of the weights, the weight times the input, and we add a thing called a bias, and then we apply this activation function f, and this is what our output y is for every single neuron. So a lot of the things which you'll see, we'll get to it later, but there are hundreds of thousands of neurons, or millions, or billions, or very, very large numbers of neurons to do different tasks. And you can get really good performance just by doing this. So at those f that we talked about, called an activation function. Here are some common activation functions you'll typically tend to see. Sigmoid is great for classification. There's also ReLU, which is on the right. Sigmoid just maps everything essentially between 0 and 1. And then ReLU can, essentially it's everything that's negative is 0. Otherwise, it's just whatever the input was. So here's what neural networks look like on a graphical level. So we have some sort of input layers. So this would take in, this is essentially would be a mapping from R3 to R1, or just a real number. So what this could be is there a cat in this picture? So I have like 3 pixels that represent my picture. Not a great analogy, but it is. And then we have some hidden layers here. And this is a fully connected network because you can see this neuron is connected to every neuron in the next layer. And then this neuron is connected to every neuron in this layer. The connections represent weights. So you can see 1, 2, 3, 1, 2, 3, 4. And this, essentially what you do is you do all those calculations, you add it up, you apply your activation function, and then you shove your activation down all of these tubes effectively to the next one, and you just keep propagating it forward until you reach the output and you get some sort of reasonable output. So to kind of walk you through this, we're going to be doing this. So what you're seeing here is, here are our 2 inputs. So we're mapping from R2 to R, since we have 1 output. We're trying to figure out what the output is. So we have, the input is 2 and 5. We have the weights here. So this is a weight of 1, this is a weight of 6, this is a weight of 3, a weight 5, 7, 4. And then these are the actual bias. So the first one has a bias of 1, bias of 9, bias of 6. So the activation I'm going to use is just take mod 10. So just divided by 10, what is the remainder? So you should only get a single digit out of it. This is just to make sure that the numbers don't get increasingly large, and I don't have to do any like floating point math. So never try to use this activation function. I don't think it's actually useful. So we're going to calculate this one. So what we do is we have our activation, which is 2, times our weight, which is 1. We have our activation of 5 times our weight of 5 is 25. So you see down here, 2 times 1 plus 5 times 5 plus 1, which is our bias. Mod 10 is equal to 8. So the output of this is 8. We do the same thing for the next one. So 2 times 6, 5 times 7, plus 9. Mod 10 is 6. The same thing. And then we're going to do the exact same thing on the output as well. And this is just the basic idea of how a feed-forward network propagates. So let's talk about activation functions. If you were sitting there and wondering, why do we use an activation function? Because it does this thing, the technical way of saying it is it imparts nonlinearity into the network. So, and what that really means is that if I start propagating that network forward, it doesn't matter how many hidden layers I have. If I'm not using an activation function that imparts any nonlinearity, if I'm just combining linear combinations of functions, all I get at the end is another linear combination of functions. So this is what I mean on the right. So I have a function f and a function g. And if I apply f of g, I still end up with something that's linear. I never could get x squared. Doesn't matter how many times I add another linear function to this, I will never get x squared. And that's all I'm saying here in this slide, is that you need to do that in order to represent interesting new functions like x squared, x cubed, x to the 4th, like arbitrary polynomials. So we're going to talk really quickly about convolutional neural networks. So as you can see, we kind of have this inputs, we have some hidden layers, and we have some outputs. And this structure will always be there for whatever neural network we're talking about for the most part. But So a long time ago, they were like, hey, we would like to use neural networks. They're really good at classifying certain types of data, but they're not great at classifying images. Because what they would do is they would take this image, like I have here. So this is a 3 by 3 pixel image, effectively. And then it'll take it into a single linear map, and like an array, effectively. And then you would do that as your input vector. So you'd have an input vector of 9, and you just fully connect everything and just slide it forward like that. So the issue you have is that if something is classifiable based on a smaller area, it being in the right-hand corner versus the left-hand corner is entirely different, which is wrong. If I have a cat in the top left-hand corner of my image and a cat in the top right-hand corner of my image, they're both still a cat, and I should probably treat them similarly. But this one doesn't allow for that structure. So that's what we want to do for convolutions. So essentially, what we're going to do, I have a lot of graphics here. We have this thing called a kernel. So it's kind of hard to see, but we essentially we're taking 3 by 3 and converting it into a 1 image. So this one up here, you have 1, 0, 1, 0, 1, 0. It's essentially an X is the actual, an X of 1s is the actual kernel. So we apply it to, we take the first part of our kernel times this one, 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 and we get out 4. So you can apply this across the entire image. And the output of what you get is a slightly smaller image and a little bit more concentrated feature density. So this is what you'll see on the bottom left. This is a common thing looking for essentially lines and edges. So that's what the kernel is. But you never know. Usually you apply more than one kernel. And this is what generates a feature map. So what you see here is the kernel is this little image. This is their source image. We apply a convolution with that kernel across the entire image. It's really hard to see because it's moving, but there's actually using 2 different kernels. One is essentially slanted to the left, and one is slanted to the right. And what they do is they generate 2 different feature maps. So slight variation of the kernel, 2 completely different images based off of it. And this is what we tend to do a lot. So we get all these different feature maps. So you have something that's either the same size or very similar in size to the image previously. And you have more of them because you applied multiple different kernels. And then we can do a step called pooling. So what we're doing is essentially downsampling the image in a way, but in a way that makes sense based on whatever our task is. So what you're seeing here is a thing called max pooling. There's max average sum. So we're just looking over these 4 points, and whichever one's the highest, that's what we're putting down here. And we're going to take something that is 4 by 4 and convert it to 2 by 2. So this is kind of the whole structure of what a convolutional neural network does. You take an input image, you apply your kernels in a convolution, you get a bunch of feature layers. You take those feature layers, you downsample them using pooling. You then flatten out the actual thing, the different features, the actual different images, the downsampled images, and then you apply that into your neural network just like we used to do by linearizing the whole thing. So this is a nice graphical representation. You'll have these slides. Just quickly switch to share a different screen so we can kind of walk through this process. Okay. So what I have here is I can essentially draw an image, a digit. So we're doing this thing. It's an MNIST data set. We'll get to it later. I'm just trying to figure out, based visually on what I'm seeing, what kind of image is this? So I'll draw a really bad 3. So as you can see, it thinks it's a 3. This is the downsample drawing. It's the second guess. It could be a 7. Not sure exactly why, but that is what it is. So you can see here, we have our first convolutional layers. So we're taking this image, and for this pixel, we do a 5 by 5 kernel. It's kind of hard to see, but essentially this pixel is made up of all of those pixels at the bottom right. Then we'll do the same thing again, but this is with a 4 by 4 kernel to downsample even more. And then this is what we're looking at as our pooling layers here. So we're doing combinations of these different images to combine into this feature. And then we'll do it again with a smaller kernel. And essentially, this is your feature vector that you actually end up with. This is what we end up linearizing. So this gets connected to one long chain of images of essentially pixels. And then that gets fully connected to the next layer, which is what you see here. And then this gets fully connected. And then finally, you have your 10 outputs of 0 through 9. You can kind of see the different color intensities represent the essentially the weight, how much is the actual activation of those individual pixels is. This is linked in the power presentation. If you're not exactly following everything I'm saying, I think it's really good to just step through this. This is a really great resource. Back to correct. I really hope I didn't drop out of the thing there. We'll just keep going and ignore everything in between. It's fine.
Looks like your screen share is down.
Yeah. It shut. Microsoft Teams crashed on me. I'm really surprised it didn't get kicked out.
Exciting.
Cool. We're back. So we'll talk about a thing called, so there's a lot of different error metrics. So back to the kind of the high level idea of you have some sort of known value from your data set, you have some sort of predicted value from a machine learning agent, you're trying to figure out what the error is. Could we do better? Could we not do better? Whatever it may be. So we have our vector that is in Rn, just means that we have n of them, n is an arbitrary number. We have y, which is the dimensionality of our output. We have y hat, which is our predicted output with the same dimensionality. We have some sort of k, which all that symbol stands for is positive number because it represents the number of data points. I don't know how you train with a negative number of data points, but that's beyond the scope of this presentation, I assume. Dumb joke, sorry. So we do this thing called mean squared error, and it literally stands for exactly what it seems like it would stand for, mean average. So we're going to do an average squared. There's a square, and then the error is the difference between your predicted and your actual output. So this is kind of a really common way that you're going to figure out the error of your network, and you want to average it across multiple samples because some samples you do really well on, some samples you do really bad on, but what you want to do is better on all samples collectively. So I talked a little bit about forward propagating neural networks, and the question you guys should all be having is, okay, you can forward propagate, you can do all this fun convolution stuff, we can figure out some sort of error metric. How do we figure out what the weights should be? And that is a really hard question. There's a video that I linked here down at the bottom by 3 Blue 1 Brown. He does some really great visuals, which will probably be better than anything I can do, so I'm just going to link you there and not waste your time. Essentially what we're trying to do is figure out for every, essentially you have some sort of error, you have prediction, you want to figure out what are the derivative of the error with respect to every single weight of your neural network, and then you change your weight in the correct direction, which is why I'm not going to go into super in detail, but essentially what you can think of it as every weight contributes to the output in some meaningful way. What I want to do is figure out is how do I change that weight so that my output is more correct, while at the same time not ruining everything else at the same time, all of my accuracy on the other weights. So like, again, a little bit more mathematically, you have some sort of theta, which represents your weights and biases. You'll see this notation all the time. You'll see an alpha called a learning rate, and then this C kind of like your function, this could be mean squared error, essentially what's your representation of error. So what you want to do is you want to take your new weights, which is theta of I plus 1. You can think of I as essentially indexing in time. You have your old weights, which is theta I. I want to move in this direction of the gradient of that. And all that means is that if I can decrease this weight and get a better answer, I should. That's it. There's just some fancy math saying that. So here's kind of a good example of what I'm talking about more graphically. Essentially, what we want is this little red ball. You can think of it just like a little slope, just like you would like roll it down a hill, and it'll get stuck somewhere. Essentially, what we want to do is do the same thing with our neural network programs. So this wavy line essentially represents accuracy. So if we're at here, or I guess error, if we're here, we have a very low error, so a very high accuracy. We're doing really well at our task. And you'll kind of see landscapes like this with respect to optimization all the time. And all you're trying to do is get to the bottom. But your only information that you have is whatever place you're at, you can sample what the actual derivative of this slope is and move in that direction. So if a really high learning rate, because remember, we're multiplying the learning rate by our step. If you have a high learning rate, you tend to jump around a lot. So for here, I'll jump to there. Since it's still going down in that direction, I'll keep jumping, but then I'll go back, and you kind of jump around, and you never really land on anything. This means your learning rate is too high. If your learning rate is too low, what you'll end up doing is taking very small steps, and it'll take you forever to actually converge to any point that's meaningful. If the learning rate is pretty good, what you'll do is you'll jump around a little bit, but pretty quickly you'll settle in on the exact point. So it seems pretty straightforward when you're talking about these kind of really simple examples of like 1D, essentially optimization. But usually things start to look like this. And this is just the 3D representation. What we're really talking about is like 10,000 dimensions. Because remember, every single weight is something that you're minimizing with respect to. So you have this very complicated error function with this weird, arbitrary like landscape that you're trying to optimize over, and you're trying to find the absolute global minimum, which is a very hard task, and there's no way to know that you've reached it. All you know is what my value at the current position is.
Jason, I think it might be good to just clarify what the axes are here, what the X and Y and Z, so to speak, are.
So Z would be the actual, what's your error, or how your accuracy, sort of, the inverse of your accuracy, so error. So what you want is to be at the bottom. So if you're up here, you have a very bad neural network. You're predicting the wrong answer all the time. If you're here, you have a very good neural network. You're mostly predicting the correct answer. And these are just kind of like a general representation of, like, as you move your weights, where would you end up in this space? This would just be like a 2-weight neural network because it's in 3D.
And then we also had a question in the chat that I think would be good for you to talk about a little bit. So somebody asked, do you tweak the learning rate in different iterations or just hit it and trial it?
Both. It depends on what you're doing. What we're going to do today is just one learning rate for the entire time, but there are different optimizers that dynamically change the learning rate based off what you're seeing. And you also do like random restarts where you'll create random neural networks multiple different times to start from different places. And this is kind of the open question in how to properly do this in machine learning. There's not like a single answer. There's pretty much anything you could think of, people have tried or not tried. And if you think of something new, you can write a paper. It's going to be super fun. And then you just get into all these, how do you balance this trade-off of, I want to search the entire space, but at some point I would like to converge to something that doesn't suck. And this is kind of the really hard problem in machine learning. That cover the question?
I think that does cover it. Thank you.
Cool. So some practical issues. Remember, data is king is the way I like to think of it. Your algorithm will only learn what's in your actual data set. Remember how we were doing that decision tree with the mod 3, and it learned an incorrect mapping just because all it had ever seen, it could make rules that did not represent the actuality of what was happening. If there's bias in your data set, it'll learn that bias. If there's a low representation of certain outputs, it will probably not learn that output. If I give you 10,000 pictures of a cat and 1 picture of a dog and tell you to learn how to classify the difference between the two, most likely what it'll do is just say everything is a cat, because on average, it'll still get a really high score. And this is kind of an issue. So there's a thing called out-of-sample data, which essentially means, well, a good example is what I just said, where you give something that is very different than what you're normally seeing. So this is an issue with autonomous cars a lot. They work really well in the daylight, but as soon as you're not in the daylight, they're now running neural networks that were trained on daylight data at night, and things look different, and then they don't know what to do. So how to properly generalize is a really big open problem. So here's an example of what I mean more specifically. So let's say we had this decision tree that we trained earlier. I give it a horse. A horse does not have feathers, and it does not have fins. So it must be a cat according to this decision tree. And this is just because it never saw a horse, and it never learned to distinguish a horse from a cat, because based on 2 characteristics, they're the same thing, so therefore they're the same thing. So what you can also do when you're training, so you start off with this data set. So what you're trying to do is make sure that your training data set matches your testing data set, but at the same time, you want to make sure that you don't train on everything that you have, So you can have some way of measuring how well your neural network does on outputs that it has not previously seen. Because what you'll see really quickly is it'll learn it could learn the entire data set and just output the exact values, and it learns no function mapping, which is useful. So a lot of things, you'll hear this thing called cross-validation. But essentially, the high-level idea, you have a data set, you split it into a training and a testing data set, you train on the training, and you test on the test. That's it. So you have this split. We validate on the untrained data set, and what you'll see is this is essentially a thing of loss, which is similar to error. So the error goes down over time, and what you tend to see happen is your network will get progressively better, essentially asymptotically approach zero on the training data set, and at the same time, the validation data set will remain the same, if not go up, because it'll start to overfit and look specifically at features that are only in the training data set, but do not represent the entire holistic view of the validation set. So each round of training is called an epoch, and you can see epochs going across the bottom. So let's talk about the curse of dimensionality. So I talked a bit about you need to see enough examples of something in order to learn how it's different from other things. This is pretty straightforward when you have in only one dimension. So if I just have these dots on a line, essentially, you can see I cover most of the line just based on these small number of dots. But what happens if I add a second dimension? So this is the same number of dots, but at the same time, now I have this gaping hole like here and here and here, and I'm not covering the entire data set. What if something is very different in this area and I just don't know about it because I haven't seen it? And then this applies even more to the third dimension and to the fourth, to the fifth, and so on until whatever high dimensionality thing you're doing. So this is the curse of dimensionality. The more dimensions you have, the less you're going to see of examples of that area. So what you could be looking at is like some miscellaneous outlier data point, and you think it's representative of the entire area when it really is representative of nothing. And you just don't know because it's not possible to have a large enough data set to cover everything ever. So I probably used overfitting, underfitting a little bit earlier, but here's a good representation of what that means. So essentially, underfitting means that your model doesn't have enough complexity to represent the actual function you have. So the actual function we have are these black dots, 5, and what those are, they're pretty close to essentially a quadratic function. So if I try to use a linear function to represent these, it doesn't matter what parameters I choose, it'll be bad. Because like no matter what you do, you're only going to get a certain level of accuracy before it's just like you just can't represent a curve with a straight line. So if we do x squared and fit the actual underlying structure of the data really well, you get a really good example. And then here you have on the far right, you have what overfitting is. This is essentially, it learned exactly what the points in the data set are, but if I started sampling more points from this actual value, you'll get points essentially along these kind of lines here, which obviously do not fit what the hell this is at all. So this means our model is way too complex and essentially just memorized the data set rather than actually learning anything useful. You'll tend to see these in your loss and training validation curves. So what you'll see is, essentially your error. Is if you don't see essentially the validation start to go back up in accuracy, or if the training data set seems like it keep going down and the validation data set seems like it keep going down, you probably haven't learned enough yet, and you should keep trying. Maybe look at more complexity. You're just kind of like not seeing a lot of progress. You're not seeing that really nice curve. So this is what overfitting looks like. So if you picked a network right here, obviously you've overfit pretty badly. You're now looking at essentially making decisions based off things that are only representative of your training data set and not your test data set. As you can see, the test, like you do real well in the test, but this validation that it's not actually training off of, it starts to go up. This is a good fit, and what you honestly usually want to see is you want to get it to overfit a little bit, and then pick the model about when it started to overfit. Because this model is probably the most representative of, that you're not going to learn anything more with the current model, but at the same time, you're not overfitting to your data set. So though, as I talked about, we're doing all these computations, and we're talking about millions of networks and very large number of neurons, whatnot. How do we do these computations efficiently? And that's where GPUs have been so successful. You can essentially, the Mythbusters did a great analogy here with, they have essentially a single paintball gun on a dolly that shoots around, and it can shoot this image. And it takes a while for it to do it, but it can do really complex things because it's a single gun that's pivoting around. This is more what a GPU is like in comparison, where you're just going to do everything at once. So you can think of a GPU as a bunch of small CPUs that can only do simple things that all operate in parallel. So here's the fun part of machine learning, is that you don't always know why it chose what it chose. That's why decision trees are great, because I can look at a decision tree and be like, oh, I can see exactly where I went wrong. With a neural network, especially a large neural network, you have no clue. So here's a great example of, we have a panda down here, and what we're doing is we're taking this random noise, we're scaling it down so it's essentially not even noticeable, and then rerunning the neural network. As you can see, I can't even tell a difference between these two images. But according to the neural network, this is a panda, and according to the neural network, this is a gibbon. And we have no idea how to fix this or how to solve it. This is especially problematic. There's a lot of like autonomous car stuff that I can like take a single red pixel, and like if I kill that pixel, everything just kind of craps the pants. So there's a great XKCD on this as well. So we're going to be training our own neural network today in the actual exercises. I went a little bit long. So we're going to be looking at a data set called MNIST. And what MNIST is essentially a bunch of handwritten digits, just like the example I showed you earlier with that convolutional layers and whatnot. So you're going to get a bunch of these, a couple thousand. You're going to train those into a neural network that's going to classify them based on the images. And then you're going to move on, because this data set is pretty straightforward. It's kind of the hello world of machine learning. You're going to move on to KMNIST, which everything in this row is the same character. Everything in this row is the same character, and so on. There's 10 of them. As you can see, there's a little bit more variation in the second level of the data set. So I'll walk you guys through that with Google Colab in a second. While I switch, I'll let you watch this fun video. So this is essentially the same thing. This is based off some research that PhDs that I worked with have done. So what they're doing is autonomous driving here. And essentially what they're doing is taking this image, just like you guys have been doing, what you're going to do in a second. You create a neural network, a convolutional neural network based off this. You output some value. For them, it's a cost map. So this is what the output, the top-down picture of the cost map looks like based on this image. And they're able to do that in order to drive around the track. Right. Cancel out of that one. And now you should see what you're going to see. So this is a Google Colab notebook. Essentially what it does is it allows you to run the neural network from your Google account. So what you'll do is you'll have a link to this based on the write-up. You'll add it to your own Google Drive. There should be a button at the top that's pretty straightforward. And then all you're going to want to do is hit Run All up here. It'll take a little bit the first time because it has to install some files and get some things set up. But through the magic of presentation, that is already done. And all you're going to do is essentially, if you want to rerun something, you can just click that. It might take a minute here. There it goes. It probably just needs to get kicked. So you'll just do the run all just like I did, and it'll slowly make its way through this. But while it's doing that, I'll explain some of the things we're looking at. So this right here is defining the model. There's some write-up that corresponds to this and what exactly you guys should be doing. We're using a single convolutional layer, so we're using 32. We're expanding it and doing 32 feature maps. So you take a 28 by 28 image, which is what MNIST has. You generate into 32, and then we're just directly flattening it from there and doing 2 layers. So it's a little bit more simple than the really fancy one that has the nice graphic. Essentially, what you guys are going to be playing with are the 2 values right here. You're going to have the learning rate, and you're going to have the number of epochs. and you're going to be playing around trying to get different accuracies on this thing and kind of get a feel for what it's like to train a neural network. Too bad. So while this is running, if anyone has any questions, feel free. It's probably going to take forever. But that is the core part of the presentation. I have, please, this is kind of the first time we're doing this. So if you guys have feedback, if you didn't quite understand it, if I went too fast, whatever it may be, please let me know. I'd love to make it better for the future.
All right, and Jason, you want to, can you put a link to this? Actually, I'll just put the link right now in the chat to the instruction document, and then I'll also send it out in the email after this meeting.
Awesome. Pay close attention when you're working through this exercise. Pay close attention to. You can kind of change these learning rates and number of epochs arbitrarily, but I kind of gave you a range of what you should change them to, so you're not just hopelessly searching hyperparameters at the end of the day.
Just because someone, oh yeah, sorry, a couple more questions that people asked. So someone asked, what is classical versus deep? Because I mentioned that in response to a different question. Classical models are things like decision trees or support vector machines, which are something that we didn't talk about today, but it's another more complicated way of classifying things. Basically, things that don't just use this technique of sort of trying to approximate this giant massive function through backpropagation, right? Deep learning and sort of neural networks and that whole umbrella is essentially where you stack a lot of layers together and then use this neural network model to train a model to give you a function approximation. And another question was someone saying that they had trouble understanding the fundamentals of machine learning. I don't really know what questions to ask, so what do you recommend? So just as a starter, if you listened to this and were confused, that is almost expected. This was a lot of information in a very short amount of time, and the idea of this presentation was more to give you an idea of the gist of what machine learning can do, rather than get you super ingrained in the nitty-gritty details. The practice problems should give you a little bit more to work with, just so you can learn a little bit further. But other than that, if you actually are interested in learning more about this, I think we've compiled some resources, and we'll definitely be happy to put together more resources. I think that's a thing that we've been trying to do as older members in general, just compile resources that you guys can use to learn more if you're really interested in a particular topic. So,
yeah.
Jason, do you want? I don't have any promises on that because we haven't compiled those resources on this particular subject at this point, I think. But
we'll do the best that we can.
we'll try to put something out. I'm not going to promise that I'll send it out in this week, but I'll try to get some resources out on this, because there are a lot of good resources online, and there's also a lot of not so good resources.
To answer the next question, was you supposed to know anything about machine learning before coming to RJ? No, no one does, for the most part. There's one, it's the blue moon, a kid comes in knowing what a neural network is, but for the most part, no. This presentation was supposed to be like drinking from a fire hose, in order to understand kind of the general framework of what we're looking at, so that from now on, if you're like, well, okay, I still don't really get what the point of an activation function is in a neural network. Hopefully from this presentation, you can ask questions like that and get a little bit more specific in the information you want to know. And then hopefully that is the correct way or a good way of doing this. We're trying to speed you guys through a bunch of stuff because tech's curriculum isn't super great at getting to this quickly.
Yeah, and one more question that's actually a really good logistics question. My repo doesn't have project1.4. How can I pull it from the template? You don't actually, so because we're using Google Colab for this exercise, you don't actually need to have this in anything locally on your VM. Everything will go through Google servers. So if you follow the instructions that on the markdown file that I sent you, that should contain information on how to make a Colab notebook that just is a copy of JSON's, just to get started.
Mhm.
So yeah.
So
And
really quickly before other questions, because my thing is finished. Essentially, well, you're talking a lot about changing the learning rate. So if I wanted to change this like e to the -5, I would change the value here. I have to rerun this by clicking that button, and then I have to rerun this by clicking this button as well. So just make sure to rerun both, and you'll see the actual output here. So we take, essentially when we first start off the network, we take in this image of a 7, and here are essentially a histogram showing what the probability that we think this is a 7. So when we first start the network, it has not been trained, so therefore there's essentially an equal probability of it being every digit, because that's how randomness works. And then after a single iteration, you'll see a giant step up. It's going to be very confident in what it's looking at. And then you can also plot out some nice graphs of your training error versus your testing error.
All right. Jason, do you have anything else that you want to be recorded, or can I cut off the recording now?
I think that's it.
All right.